Welcome to this video series on how to design an impact wrench adapter for use with a cordless drill. In the two previous videos we modeled the 3D parts, made the 2D production drawings and performed a dynamic simulation of the impact mechanism in Siemens NX Motion. This last video of this series will show you the manufacturing of the parts and assembly of the impact wrench adapter. At the end, the design will be tested and we will see how it performed in practice. The manufacturing of the parts is done at the Mechanical Engineering Workplace at HAN University of Applied Sciences located in Arnhem. The production facilities that are available at the workplace include a water-jet cutting machine for cutting through metal plates, several lathes for turning metal and plastic workpieces, manual 3-axis milling machines, a CNC 3-axis milling machine, MIG, MAG and TIG welding booths, and other machinery such as press drills, a hacksaw and bandsaw machine, a spot welding machine, belt sanding machine, bending machines, measuring tools, etc. Most work was done on the lathe. The lathe was used for making the drive shaft, flywheel hammer, square tool drive and the spring holder ring. The turning process makes it especially suitable for cylindrical parts, also with tight tolerances such as bearing seats and other fits. Here is a time lapse of the turning process. The milling machine was used to make the flat faces on the square tool drive and the drive shaft. Unfortunately, there is no video footage of the milling process. The CNC milling machine is suitable for making complex geometry that is almost impossible to do manually. The non-cylindrical details of the flywheel were produced on the CNC milling machine. These are the two hammers on top of the flywheel and the two V-grooves. The V-grooves of the drive shaft were also milled on the CNC machine with a ball nose and mill. The water jet cutting machine is used for cutting the contours of the anvil from a 10 mm thick steel sheet. The pressure of the water jet is set to 2,800 bar and the abrasive rate is set to 200 grams per minute. The housing of the adapter is 3D printed at the Fab Lab of the university. The printing method is fused deposition modeling on an Ultimaker 5S and took about 34 hours to complete. PETG filament is used because this is durable, impact resistant, chemically resistant and still relatively cheap and easy to print. These are the parts that have been manufactured and can now be assembled. The parts already have some lithium grease on them, so we don't have to do that during assembly. Here we have the 3D printed housing which will contain the mechanism. Next we have the input flange of the housing. It already contains the ball bearing, which fits tightly. Then there is the output flange of the housing. This already contains the ball bearing and the square drive for the sockets. The anvil is already connected to the square drive with green Loctite 648. The O-ring is also placed onto the square drive. This is the drive shaft. The spring holder is pressed onto the shaft with a hydraulic press and welded on the bottom for extra security when the spring is under compression. An aluminum bushing is slid over the drive shaft to fill the space between the spring holder and the thrust bearing, because the length deviates from the CAT model. Next is the flywheel. You can see the two hammers on top and the two V-grooves inside. Lastly, there are the parts that had to be bought. These are the two balls for the V-grooves, the spring and the thrust bearing for rotation of the spring. First we assemble the thrust bearing, spring and flywheel on the drive shaft. We use a bench vise to compress the spring. With the spring compressed all the way, it is possible to put the steel balls in the V-grooves. The spring can now be released and the flywheel is locked onto the drive shaft by the balls. Now it is possible to assemble the housing. First we put the output flange that already contains the bearing, square tool drive and anvil into the housing. The mechanism is put in the housing and is centered by the hole in the square tool drive. The input flange fits on the other side of the housing. I ended up making 2 extra backing plates for the flanges to distribute the uniaxial load of the spring better onto the bolts. These backing plates have the same contours as the flanges and are water jet cut from 2 mm thick steel plates. All we have to do now is tighten the bolts and nuts and we are done with assembling. Here we have the completely assembled impact wrench adapter. If we put it on the scale, we can see that the total weight for this prototype is 1,853 grams, which is below the limit of 2 kilograms. Now that we have assembled everything, it is time to finally put the design to the test. Let's connect the adapter to the cordless drill and see what happens. The very first test is tightening a nut on low RPM to see if the mechanism works correctly. The second test is tightening a nut on high RPM to see if the mechanism will still function correctly. This also gives a first indication of the output torque. Based on the force I had to apply with the wrench to loosen the nut, I would say it was torqued down to between 50 and 100 Newton meters. To get a more accurate reading of the output torque, the next tests are loosening the nut that is torqued down with a torque wrench. However, when putting the cordless drill in reverse at the first attempt, the mechanism locked. After taking the mechanism apart, it looked like the V-grooves already had some damage. Filing down the edges of the V-grooves seemed to temporarily fix the problem, so the mechanism was reassembled. This is the new attempt to loosen a nut torque down to 100 Newton meters. It failed the first try, but after trying it again the nut came loose. It did not go as smooth as expected, so the next test would be to loosen the nut torque down to 120 Newton meters. Unfortunately, the drill chuck was shaken loose during this attempt. After trying again, the mechanism instantly locked again and no further testing was done. I first tried to unlock the mechanism by applying more input torque by hand. This worked for turning counterclockwise, but for turning clockwise the mechanism was locked. Let's take the assembly apart and see what causes the mechanism to lock after having been used. The flywheel is stuck on the drive shaft, even after removing the balls from the V-grooves. I had to pull and rotate at the same time to get it loose. This already indicates that there is damage to the shaft and flywheel. When we look into the V-groove of the flywheel, we can see that there is indeed protrusion or galling where the balls contacted the groove surface. This is especially visible at the bottom of the groove. There is a lump where the ball impacts each time the spring is released. When looking at the drive shaft, we see the same problem of galling and a lump on the bottom of the groove. This causes the flywheel to lock on the drive shaft. The main solution for this problem is the use of hardened steel with better properties, such as a higher yield strength and better galling resistance. Unfortunately, we could not use this hardened steel and were limited to the use of low-end construction steel. An extra option would be to decrease the slope of the V-grooves while increasing the stiffness and preload of the spring. This results in less impact force of the balls in the bottom of the V-grooves, because the hammer will hit the anvil before the balls have time to reach the bottom of the V-groove. The impact speed might also increase in this case, resulting in higher torque. The horizontal groove that connects the two grooves could also be made shorter, reducing the ball impact when the direction of rotation changes. We proved that the impact wrench adapter in combination with the cordless drill could provide a breakaway torque of 100 Newton meters. This is much less than the predicted output torque from the dynamic simulation, so it seems that the simulation input is not correct. Therefore, it is always good practice to verify your simulation results, especially if you don't have much data and experience. I hope this video series was helpful to give an insight into a design process and that some videos can help with making calculations, making a CAT model or running simulations. Check out the other videos if you haven't seen them yet.